today under the general organic chemistry we are taking the isomerism, in that also specially under the stereoisomerism. In the last class we have seen the conformational isomerism and the geometric isomerism. Now, this is the third part of the stereoisomerism, that is optical isomerism. Optical means something related to the light, isn't it? So, the isomerism is also indirectly related to this light and its property. So, here when we get this type of the optical isomerism, the requirement exactly you can go on define as you go on understand more and more, the requirement may be slightly changed, but at fundamental level, at a level 1, let us say, at this stage we say that there is a carbon with 4 different groups. This is the first the low level understanding, that is whenever a carbon is specifically it is sp3 hybridized having the 4 groups. These 4 groups, one of the group can be hydrogen, an example, this can be hydrogen. The other group can be deuterium. You can have a 1 methyl group and we have a chlorine, for example. Or you can have all the 4 can be groups like chlorine, fluorine, bromine and the iodine. Or you can have a carbon with all the different groups, like one is methyl group, one is C2H5 group, one is C3H7 group, one is C4H9. In all the cases, the compound is fulfilling this condition, that is the hydrogen in its isomer deuterium, tritium is also allowed to take as a new group. So, all the 4 groups should be different, all can be alkyls or some hydrogens and the halogens, all functional groups you can have. In such a case, the compound you cannot cut into 2 halves. So, therefore, the requirement I redefine, the compound should have not only this type of this one, but you can understand second level, that is the molecule which cannot be cut into 2 halves, that you can say unsymmetric. Unsymmetric is the real criteria. Even in the symmetry also we can further study and say that the compounds which are not having the SN symmetry, no SN symmetry is the actual requirement. It is not the C2 symmetry. Compounds can have a C2 symmetry. This is the higher level of understanding, but let us start with the low level of understanding and see some compounds, introduction, properties and all that. Then at the later stage, what exactly unsymmetric or what exactly this n-fold axis of alternative axis of symmetry, we will see this. First, let us take some examples, like a compound with having the 3 carbons with carboxylic acid, it is propanoic acid containing a OH, and the rest are the hydrogens. Now, this compound has one eligible carbon, that is in the central carbon you have one hydrogen and the COOH and the OH and the methyl. That means all the 4 groups are different. Then this compound is eligible to show according to the low level understanding, and this carbon is oftenly given a star mark so that we can recognize, oh, this carbon, due to this carbon it is going to show this optical isomerism. And this carbon is also called a chiral or chiral carbon, or it is also, you can say, because it produces unsymmetric, so therefore it also called asymmetric carbon. Asymmetric carbon. Symmetry, it is not allowing that carbon with 4 different groups, no symmetry is allowed except C2 symmetry. Therefore, the compounds with this carbon is said to be a chiral carbon or chiral carbon. Simultaneously, you too can say this is the carbon asymmetric producing carbon. And whenever such a condition is fulfilling, the compound shows optical isomerism. In the conformational isomerism, we have seen the compound which is overlapping type is called syn, and the groups opposite is called anti. So, the nomenclature we have given to the isomers is syn-ethane, anti-ethane. Compound is same, but syn-ethane, anti-ethane. In the case of geometric isomers also, 2-butene. 2-butene can exist in the two forms, 2-methyl same side, cis-2-butene, opposite side, trans-2-butene. In that case also compound is same, that is 2-butene. In both the cases 2-butene, but the groups same side we said cis-2-butene, otherwise it is trans-butene. Now also this compound is called lactic acid. There is another lactic acid which exists as its isomer. What is the structure of that lactic acid? How do you represent that? Means by way of writing normal procedures, writing the straightforward, this type of the structures are not allowed. The molecule has a 3-dimensional carbon. So, this specifically you need a models which is able to represent the 3-dimensional the criteria. So, therefore, we have to either follow this the Fisher model or the 3D model or the Sawhorse model or this the Newman model. Only these 4 models are allowed, but not this structural or the molecular formulas. By representing you cannot write this one. So, this compound may be written using the 3D model. Let this carbon is imagined on the carbon plane, and one of the group, that is COOH, I will write. Can you write the OH on the top? Means yes, you can write, but as per the IUPAC nomenclature, the 1 goes to the COOH. Let us keep the number 1 group on the top, and out of the remaining 4 groups, 1 group can come into the same plane. Now, the carbon, COOH, another group. What is the other group you take? Means mainframe better take. Mainframe is now the COOH, carbon and the methyl is on one plane. Out of these 2 groups, 1 comes in front of the plane, 1 goes to the back side the plane. So, therefore, out of these 2 you can have an option now, either of the H or OH you can put. So, let us have a OH in front of the plane, hydrogen is going back side the plane. Now, how many groups are there on the plane? Means middle carbon, COOH, methyl. This model is called a 3D model. 3D models are a wedge and flying we are showing, therefore, it is also called as wedge flying model. Wedge flying model. The model is specifically used whenever the 3-dimensional carbons are used. So, specifically for optical isomerism, this is the one of the best practice, 3D or wedge flying model, in which now regarding this model you can pass the 4 statements. One is the carbon and these 2 groups are on the same plane, that is on the board plane. The OH is in front of the board plane, the hydrogen is back side the board plane, and in between any 2, either HOH or OH methyl or methyl COOH, the bond angle is same and it is occupying the tetrahedral model. So, therefore, now this is the one lactic acid. Let us imagine there is another lactic acid which is exactly mirror images to this one. What exactly mirror image means? Here we have to understand one point. Mirror image means if I put a duster in front of the mirror, in the mirror you find a duster. So, any damn item will produce its image, that is called mirror image. But that mirror images will be found to be identical in many cases. Only very few cases, if you observe, for example, if I put my left hand in the mirror, you find right hand. That means image is not identical. Original one and the image is not identical. You are getting another image. Like that, this compound also, if you put in front of the mirror, in the mirror you find another compound, not this one. This is only possible in certain cases. Most of the compounds will produce the same compounds which have all the properties same. But just like the right-handed, this called right-handed, the other hand as a left-handed, right shoe, left shoe, right gloves and the left gloves. This handedness, if it is different, we are able to get the new one. What will be the structure of that new one? Means carbon will be same, top group COOH also identical, but the here we are having a left side methyl, this will have a right side methyl, and the two groups which are there here also will have the OH will be OH side, hydrogen will be hydrogen side. Now this is a mirror image of this one. So let us call this is compound A and B. A and B are said to be a set of mirror images. They are mirror images. And they have another property. They are mirror images, but if one compound, if I take and try to put it not exactly on the top, but I want to put it in the same place where B is present, or get the B and put it in the same place where I have a chair, remove that chair in the same place where a new chair, if it is exactly, if I place there, that is called what? Superimposable. So these two are not superimposable. So we call non-superimposable. We call non-superimposable. So these two A and B are said to be, they are mirror images and non-superimposable. One will not set over the other one. In fact, if any molecule or any item, if it is exactly superimposable, those two are called identical. Identical means with all respects it is same. But these two are not identical. They are differing in one case. What is that? They are non-superimposable. But the internal distances, if you see between the OH and H and OH, same distance, they are said to be isometric. Optical isomers are isometric. Metric means the measurements of this compound and this compound is same. That's why within the molecule attractions between this A and A, same type of attractions when you observe between the B and B. So therefore, all the physical and chemical properties happens to be same except a few. So this set of mirror images and superimposable isomers are said to be enantiomers. Especially they are called enantiomers. However, in broad way you can say they are optical isomers, but optical isomers are having certain specific the internal differences with diastereomers and so on. So let us accept first this A and B are optical isomers. In that specifically, this is the simple variety having a mirror image relationship and non-superimposable, means one compound if I try to put it over that, out of these three, one group you can rotate and adjust, but the other two will become this side, that side, like this. For example, if I put it, this forefinger, if I adjust the thumb finger and small finger, imagine that this is having the three legs and one candle type, and this is another one which is a mirror image. If I put it like this, if I adjust, these two will not. If I adjust, the other two will not. Like that, the molecule will not exactly set on the other one. That is called non-superimposable. So a set of isomers which have mirror image and non-superimposable, that set is called specifically optical isomers. In that specifically enantiomers. And what properties they differ? I said because of the isometric feature, they have same boiling point, melting point, reactivity, chemical reactivity, and it's a small physical and chemical, all the properties. There is COOH. How this reacts with bicarbonate, this also will have the same acidity, basicity, all that molecules will have same, except very few properties. What is that? Different properties are properties difference. Difference in the property means one of the property is a optical property. Optical property. This property I will explain, but let us go to the another property. This is a biological property. Biological property. What is this biological property means? Most of the biological properties are concerned with the very complicated mechanism. An example, if there is an enzyme, imagine that enzyme has a cave type of the structure. Into that, if right shoe enters, imagine the cave is so specific, into that a right shoe enters. Into that, can you insert a left shoe? No. Now the right shoe, left shoe are isometric, but they are mirror images and non-superimposable. So that means this cave is only specific for right shoe but not left shoe. So a one lactic acid, for example, this enters into this one, the other lactic acid will not enter. That's why so many enzymes will have reactivity to only one compound. There is no enzyme that sets on the both the compounds. All enzymes are three-dimensional and so specific. If one, let us say D-glucose is able to react with one enzyme, L-glucose under no situation it is able to react. So enzymes are so specific. That's why on a broad way we are calling biological activity, but exactly saying specifically the molecules when have a three-dimensional difference, even the reactants like enzymes also have some three-dimensional differences. So therefore, if one enzyme suits with one compound, the other compound will not suit. You have to set another enzyme. Fortunately, the enzymes will not have a rigid structure. They go on change. Lot of flexibility will be there, just like a cloud in the sky goes on change. Enzymes also have got a lot of flexibility. However, they are well governed with the other features. So the enzyme will take up a required shape and then make the compound to undergo reaction. So the accepting this biological property, and another property is optical property, and this property is also well studied in how the two isomers are differing in this specific optical property is also well studied. So let us see how these compounds. So one compound, if it has got, let us say, a plus 35 value, the other one will have the same value but minus 35. What is this 35 and the 35 are plus and minus? A polarimeter, that's called the machine or instrument that measures the optical activity of a given compound is called polarimeter. The meter alone will decide what exactly the value, and also is it plus or minus also will be designed only or identified by the machine. By seeing the compound, we cannot guess calculate the property of the optical value as well as whether it is plus or minus also, except in the carbohydrates we can guess certain extent plus minus, but all the compounds by seeing the structure no one can guess the plus or minus value. Let us see how the polarimeter works. So let us see how this polarimeter works and how it is made up of, what is the principle involved in this meter to work. The polarimeter is an instrument that measures the optical value or the activity of a given compound. It is having the certain features, like for example, we have a first step, the light producing source of light. This light is passed through a small slit so that a beam of light is coming out. This beam of light is shown with a symbol like this, representing this light has gotten a chance of, just like a wire between the two sticks, if you tie up here and just pull and leave it, the wire will be going on oscillating, giving the waves. From this direction, if you see, the waves will be only up and down. The waves will be only up and down from this direction, if you see. But the ordinary light will have a waves in all the directions. Therefore, the ordinary light is represented like this. It is the way of representation. It is giving the waves in all the directions simultaneously and propagating or traveling one place to the other place. Such a light I am passing through. Imagine that there is a window having the grills in one direction. Literally speaking, this is not a window and there is no grills. This is a Nicol prism. This is a Nicol prism which is working as a just like a window which has bars in one directional. Therefore, the other waves will be cut off. Only one wave which is parallel to this window grills will come out. This is cutting all the waves and only one wave is allowed. This wave is called single plane polarized light. Now, this is working to produce this one, therefore, I call it as a polarizer. So, when ordinary light is passed through a polarizer, it produces a light which has got only one direction oscillations. Now, such a light is called single plane polarized light. Now, this light is allowed to pass through another window which is also having the grills in the same direction. In fact, the other grill is coincided, that is, we are arranging in such a way this light simply passes through and then comes this is same plane, it isn't it, and then reaches your eye here, this is your eye, and reaches so that you can find the light is there, right. So, this is our first arrangement. And then what we do is, in between these two, this is another prism, this is also Nicol prism, working to identify, therefore, this is called analyzer. So, there are two Nicol prisms, one working as a polarizer, the other one is working as an analyzer. And in between these two prisms, we are taking one tube which is made up of a material which is not having any action on this light, and in which we are going to dissolve our compound. This is our compound we are taking. How you take this compound means solid compounds and gases are not allowed. Solids and gases not allowed. Compound can be in the form of liquid, okay, or if a gas or solid, if you take, you dissolve in a suitable solvent so that solution is formed. So, you take the solution or liquid, but not gas or solid, not allowed. These two are not allowed. They are dissolved in a suitable solvent, liquid solvent, and then so that you get a solution. That solution you take here and again pass the same light. As the light passes through compound, this compound has one speciality. What is that? It has a chiral carbon. Therefore, by the time the light comes out of this compound, the plane of the polarized light will change the direction of the. Now, it is like this. By the time it comes out, it comes like this. Then our window is fixed like this. So, therefore, light cannot enter. It will be cut off and nothing is visible here. So, what I have to do is, I have to rotate this second window or analyzer in order to enter this light. So, by doing so, what I have to do is, this second prism is fixed in a wheel so that it can be rotated, and the wheel has got a lockups at 180 degrees right side, 180 degrees left side only you can rotate, not a thorough 360 degrees, it is locked at 180 degrees. So, which side you are rotating to see the light? One side randomly you rotate right side and see whether the light comes or not. If you are not able to get, check the left side, either this side or that side, one after the one. at one place you find the light is coming. So first observation is whether you are rotating that window or the disc toward the right or left. When you are rotating the right side in the clockwise, you call it as a plus compound or dextro compound, right? When you are rotating the anti-clockwise or left side, call that compound as a minus compound, negative compound, or levo, L-E-E-V-O, levo compound. You may give a small L letter, small d letter, or write levo, dextro, or minus or plus value. And also you observe how many degrees you have rotated in order to see the light. So the value as well as the plus or minus, this will be decided. So for a given compound, that value will be fixed, value will be there. However, it depends on two things. Now I said solid or gas dissolved and made solution. More solid is dissolved. Naturally, more molecules will be there on the way. The light passes through so many molecules, therefore more the distraction or the rotation will be there. So to check or to normalize this factor, we are taking the what concentration you are using. The always concentration will be 1 gram per 1 ml. We have to dissolve this particular concentration, 1 gram per 1 ml. And also how much length, this is the concentration term. Another one is length. More the distance, naturally light passes through more length. So we have to take a specific length. The length will be always only 10 centimeters length or 1 decimeter length we have to. Either 10 centimeters and nothing but the same thing. Decimeter, 1 decimeter or 10 centimeters, approximately this much tube you have to use. Sometimes let us say compound is very small, then you can take 1 centimeter tube and the value is 10 times doubled. Or small compound dilute solution, don't take 1 gram, 0.1 gram when you take, naturally it is the value will be 10 times decreased. Like that, not necessary to take only this value. If you take 1 gram per 1 ml and 10 centimeters tube, the value obtained is called specific optical rotation. Specific optical rotation. Specific optical rotation means this will be shown with a alpha within the brackets like this. And specifically what type of light, D and T also we are mentioning. The D represents sodium vapor lamp I am using, which contains 2 lines in the light, that is called duplet. So therefore D represents sodium light. Otherwise you have to, other symbols you have to. For temperature normally 25 degrees I have to use. Other than temperature you have to mention, otherwise leave it. 25 means leave it. D sodium also leave it, otherwise you have to specify. So with that the whatever the value plus 25 degrees let us say. So that means using so and so concentration and length at a specific temperature and the light 25 degrees, this will be for all the times whenever you take lactic acid you will get the same value. So therefore that is called specific optical. Otherwise concentration changes, value changes, therefore this compound will have this value, means there is no significance. So in order to get the standard value, we are converting this observed rotation into the specific rotation according to this concentration and the length terms and converting or normalizing into the standard value, that is called specific optical rotation. So one lactic acid, if it have plus 25, the other one will have minus 25. Again I will specify, by seeing the compound, either the functional groups or the carbons, we cannot judge this much value it is going to produce, nor we cannot judge whether it is a dextro or levo. It so happened, it is just a random observation. Okay, in the optical isomerism, let us take another example here. A CH2OH and a CHOH and a CHO. This is systematically called 1, 2, 3 prop in all. 2 and 3 we have a 2,3 dihydroxy 2,3 dihydroxy propanol Al, propane Al, aldehyde it is. It has a commercially also known as glyceraldehyde. Glyceraldehyde happens to be a first member of the carbohydrate series. It so happened carbohydrates are the food materials and it is easily available in the nature. Lot of chemistry, specifically in the Germany country, lot of chemistry on the carbohydrates at very primitive level it is studied, and much of the organic chemistry was standardized taking the carbohydrate as a first examples. So this glyceraldehyde, according to this 3D or the model, so the top one is number 1 carbon I am putting on the top, this is number 2 and this is CH2OH. I will write like this. Main frame generally we write it on a plane, and out of this HOH we write one in front of the board, one backside the board. Either one you can put OH that side or this side. This is called glyceraldehyde. What model it is? It is 3D or wedge flying model. Now, as I was discussing, by seeing the compound, can you guess the optical activity? Means it is so happened, we don't know what exactly, but it is so happened in the carbohydrates, it is possible to guess the optical rotation, that is right or plus or minus we can identify. Not the value, but we can plus or minus, dextro levo we can identify. The same molecule, if you look from this direction, the plane of the carbon comes onto the plane, these two groups goes back side, these two groups comes front side, and this making this as a main frame. So the molecule may also be written like this: carbon is on the board plane and the CHO goes back side. In fact, aldehyde goes back side and CH2OH also goes back side. These two groups are front side. So OH right side, from this side if I am looking, so OH right side, H left side. So whenever this molecule, if you write in this particular model, this is called what? Fischer model. This is what introduced by the Emil Fischer, who identified or contributed to the glucose chemistry. He who gave these particular models, made very simple. In this you can pass the 4 statements. The carbon is alone is on the board plane. The two horizontal groups, that is H and OH, are in front of the board plane like this. This is the board plane, carbon is in the board plane, the HOH are in front of the board plane, and the CHO and the CH2OH are going back side the plane. This is plane, the CHO and the CH2OH are going back side. These two are coming front side, two are going back side, only the carbon is there on the board plane. And angle between, either between HCHO or CHOOH or OH and H, opposite two groups if you measure also it will be identical. This is not 180, this is not 90, make it clear. This is a tetrahedral molecule written like this, that's all. Okay, two are towards you, two are backside. The model also can be written like this, so that you can have a now the CHO, the middle carbon need not to write at all, the OH and H. This is simplified model of the Fischer model, in which the middle carbon alone on the board plane, HOH in front of the board plane, CHO and CH2 is backside. Now, when I write this molecule in the Fischer model, if only one chiral carbon, okay, the important group, that is horizontal groups, in the horizontal groups, important group if it is right side, this is given a capital D symbol. Where from you have selected this capital D, why not S or P, means this happens to be a dextro compound. Whenever it is studied that the OH, if it is right side when the molecule when it is written, it has a dextro property, therefore capital D is given for this structure. D referring the structure, that means it is the when you write the molecule in the Fisher model, vertical groups, out of that vertical group one goes to the right side is called capital D. Important one goes right side is capital D. The dextro has another method of representing the R plus, or you can say small d. Capital D is referring the structure, dextro R plus R small d referring the property. When you take this compound in the polarimeter, you have to rotate the disc to the right side, then only light is visible. So, the D and D is coinciding, but in no other cases, so randomly maybe, but in no other cases this type of the coinciding is not possible. Only in the carbohydrates it was observed. Amino acids, there are so many capital D amino acids having the LEVO property. So, therefore, there is no strictly binding on that the property depends on the structure, means not possible in fact. Why this plane polarized light when passed through the compound, it rotates to one sidedly, means the light is said to travel in the two coordinates. And for example, if you take an apple which has got the symmetrical structure, if the light passes half from this direction, half from this direction, because two parts are identical, without any deviation light comes through. That means symmetrical molecules, if they are allowed to pass the light through them, it comes without any deviation. But this same apple, if one side is perfectly okay, the other side because of some disease it has become the other way, let us say. Now, when the same light if it is passing, so for this light, this is, that means half coordination, the distance is more, the other side coordinate it is distance is less. Just like a bullock cart having the two bulls, both are running equally or walking equally without any deviation. But if I pull one bull, the other one allow to go fast, what happens? It takes a turn. Like that, similarly, the light having the two coordinates, if they travel to unsymmetrical molecule, because of this molecule or the system is made up of with two unequal parts, it takes a light takes, that means the plane of the polarized light takes a turn because of this phenomena. So, therefore, all the molecules in a simple way which you cannot cut into two exact equal halves, that is called plane of symmetry. That is also one way of low understanding actually. The plane of symmetry is not the criteria, we will see later. So, a molecule which can be cut into two halves will have two identical parts, therefore, it will come through, okay, like this. So, there are so many examples like this having the four different groups, that carbon is said to be chiral carbon and going to show. So, one of the simplest question is, I will give the four compounds, I ask which of the compound is not able to show or able to show, means you have to search the carbon with four different groups. A carbon having double bond, not eligible at all. It should be sp3 carbon with four different groups. Then only that carbon is called chiral, then it is going to show the optical isomerism as far as the first the identification, that is the four different groups. But if you see, there are so many examples with four different groups will be there, but the optical activity will not be there. Such examples also we will see.